Yeah, nice. All right, so gravitational field is said to exist at a point if a gravitational force is exerted on a mass placed at that point, right? Very simple example. If I were to place an object and I were to place an object right on Earth, right? That object will experience a gravitational force due to gravity pulling downwards. Right? And we call that force weight. Okay, so once a mass could experience that force at any point. Once a mass could experience that force, maybe upward, downward, in most cases it's downward, right? You can experience that downward force, then around here, there must be a gravitational field. Okay? Right? There must be a gravitational field around it. And the strength of that gravitational field, we call it G. Right? G is called gravitational field strength. Right? You would have done this already. You recognize that? Gravitational field strength, that G value. That G value is what? Yes. 9.81, right? So that G value is a 9.81, right? That is strength of the gravitational field. Some of the things that we need to note is that gravitational forces are always forces of attraction. Gravitational forces are mostly negligible, unless at least one very massive body is involved. Okay, for example, our gravitational field strength, that G value is due to the force of attraction of us to the Earth. Right? So we inside the Earth here, our attraction to the Earth really is that gravitational field strength that we've been measuring. I've been using all the patterns. Yes, the direction of the gravitational field at a point is the direction of the force exerted on the mass at that point. So for example, if the force is exerted downwards, the gravitational field also exerted downwards. That's okay? All these things is already. Not aware. They gonna order now. They gonna order provide everyone. Right? So that's a gravitational field, right? Okay with that? So the strength of the gravitational field is that G value. We know, okay, well, the formula here, right? But we know that F equals ma, right? And A will be equal to F1s. So at any point in time, we want to find the gravitational field strength. What we really doing is finding the acceleration that the object will move with. If you allow it to fall free. Okay, that acceleration is the gravitational field strength. So the gravitational field strength at a point in a gravitational field is the force exerted per unit mass. Right? And we know that formula already. All right. SI unit, newtons per kilogram, or what else? Or what? Meter per second squared, right? Right? What is used to check and see if this is accurate? Or is Golang? Dimension analysis, right? Yeah. All right, nice. Right? And from Newton's second law, right? A is equal to F1m, and therefore the gravitational force exerted at a mass at a point in the gravitational field produces an acceleration which is numerically equal to the gravitational field strength, and hence G is sometimes called acceleration due to gravity. All right? It's sometimes called acceleration due to gravity. Furthermore, the units are the same. All right? So all these things you know already. Okay? So that's today, right? All right, let's fight them there. What was Darian?
He did because you can't get to pick him up now. He had the job.
Come to Darian.
Can't balance like this. I feel that I'm not going to that thing.
Oh, okay. All right, so now we want to take a look at Newton's law of gravitational field, right? So this is something that you may have done already. If I give you two large objects, right? One is M1 and one is M2, and they're separated by a distance R, right? There's a relationship that was discovered by Newton that said that the force of attraction between those masses is proportional to the product of their masses, right? Meaning that the bigger the mass, the bigger the force, right? And inversely related to the square of their separation, which basically says the further away the masses are, the smaller the force of attraction. That's okay, right? And this leads us to this nice little formula here, right? Newton's law of gravitation. All right, so if you're making little notes, add that in and add this as well, please. Right, add those two, right? G is equal to F on M, and F is equal to G M1 and M2. By the way, that capital G is what we call the universal constant. Lowercase g is the strength of the gravitational field.
So capital G is
Capital G, look at the universal, yeah, right? Gravitational constant.
certainly is what flows into percent right now.
Which one? What's that? Specific one. No, he wants to know.
Now we want to know.
Didn't you have mark it? I think that's probably there was small error there. That value should be minus 11.
Yeah, that's what I want to
I
know.
don't know, that's what I was 1 point there. Minus 11, right? All right, so let's make a note of that, right? Make a note of the formula for finding the force of attraction between two large masses separated distance r, and the formula for gravitational field strength.
And at equal.
Yeah. What's up? All right. Before we do anything else, watch this here, right? Right. Watch this here. let's say I gave you something like this, right? Let's say I gave you a large mass M, right? And you have a small mass here F, right? And I want to find the gravitational field strength there. I want to find the gravitational field strength at that point mass, right? That's a small mass, right? One is uppercase M and one is lowercase, huh? How you find gravitational field strength again? The force of attraction between the masses divided by the mass, right? Correct? Nice. So what you say? And you'll notice something after you work out this, right? This small m is that m there, right? Correct? Right. So what I'm going to show you here is the next way to find gravitational field strength. If you have separation between them and the mass of the original object. Of the larger object. What is here? We know that F is equal to G M small m on R squared. Right? If I divide F1M, small m, what happens to the m's? Small m cancel, right? So we will end up with gravitational field strength being equal to the gravitational constant by the mass of the larger object divided by the separation squared. So what does that say? It says two things. The strength of the gravitational field is dependent on two main things. The strength of the gravitational field is dependent on the larger object, the larger mass. That's this one here. That's okay. So based on how large an object is, that'll give you an idea of how strong the gravitational field will be and how far away the object is, or how far away you want to find the gravitational field strength from. That's okay. So I want you to notice that the gravitational field strength technically has nothing to do with the mass of the object, right? It has everything to do with the mass of the larger object. And one of the main reasons is that this force here, F1M, is a force of attraction. So the force of attraction is large, the gravitational field strength is large. If the force of attraction is small, then the gravitational field strength will be small. Okay? So it's important we understand which M we're using here. That's okay? So let's do a small calculation now. Online, are you okay with that? Begin it will larger. The next up. Next up. Right, try this one up. Calculate the gravitational field strength. Calculate the gravitational field strength on Earth. Calculate the gravitational field strength on Earth. Given the following quantities. Calculate the gravitational field strength on Earth given the following quantities. Gravitational field. We got good value with him after all the years now. I'm giving you, I'll just divide it in the thing that was put. So I'm gonna give you this one here.
Yes, I never do.
5.972 here. The one here now working also getting the possible. 5.972. Right, by 10 to the 24 and using radius. Right, this should give us something a little bit closer to what we know, right? I didn't like the other part. So right, use these three values to find the gravitational field strength on Earth. Right, I gave you the mass of the Earth, 5.92, 5.972 by 10 to the 14. And the radius of the Earth, 6371 kilometers, huh? 10 to the power 24, sorry. To the power 20. Whatever it is. You can technically just plug in those values, right? Should get something close, right? But yeah, remember that's kilometers, huh? That's what I can do. No. So we'll get up. Oh yeah, plug it in. Watch it again.
What? Yeah, I can ask you.
Right, plug in the right units. The answers online. Cavity, right?
Yeah. And
Oh,
R.
where Gary's?
Well, it's square R, it's a square R. Yeah.
Supposed to be 9.8, close to 9.8.
So I get that.
All right. Around 9.813, right? Done it, guys. Anybody else here online? Yeah, I didn't go. All right, nice. So that's the way you find gravitational field strength, right? Everybody get now, Sylvester? Yeah. All right. Try one more. I want to give it yield bar. I don't know why it's my bar. No. So okay, how to work it out, right? Okay. And of course, you'll recognize if you try and move to the moon, right? The mass of the moon is smaller, right? And the separation smaller as well, right? That's why their value will be 1/9 of that, probably. I think it's like 1/9 of that. It's the gravitational field strength on the moon. I don't know who worked it out. 1.6 now. I don't know, get up fast. So, right, find the gravitational field strength on the moon. Try this fast. Find the gravitational field strength on the moon. Find the gravitational field strength on the moon. I'll write it here for you, right? I'll write it back this way. Mass of the moon will be 35 by 10 to the 22. Right, 35 by 10 to the 22 kilograms. And the radius I have here is 74 by 10 to the 6. Look at I write it here for you. 35 by 10 to the 22 and 74 by 10 to the 6. Right? You can see the radius smaller than the mass. What you got? Oh, values of missing. Sorry.
Yeah.
It's 7.35, 1.74. Okay, that's that. 7.35 by 10 to the 22, 1.74 by 10 to the 6. Yeah, but point was missing. Try that back. Tell me what you get, right? Right. Katrina, check it back, Katrina. It should be much smaller than that.
What's here?
Huh?
What's here?
What's that?
What's here?
8 point something. Yeah. Okay. Guess what? 1.6. Okay, nice. Right, yeah, 1.62 around there. Or 1.63. 1.6. Alright, nice. So that's how you basically work out gravitational field strength. As I said, it's dependent on it is dependent on the mass of the larger object it's attracted to and the separation. Alright. One thing I want to point out to you is gravitation and circular orbits, right? I want to show you something from Kepler's law, but I'll do that on the code, right? I'll do that on the code in case we get lost. All right, so what is here? Let's say we had an object, right? Let's say we had an object like a satellite. Let's say we had an object like a satellite maintaining a circular path or orbital path around. But orbital is not supposed to be circular, right? At this level, we just assuming it's circular, right?
Why you rubbing it up that a good circle?
Right. So let's say we have this satellite orbiting this larger than let's say the Earth, right? Orbiting the Earth. For it to maintain circular motion, it must have a what? Must have a centripetal force, right? It must have a centripetal force, and this centripetal force is given by what? Professor, what do you think? What do you think providing the centripetal force for this satellite to make the orbit? Gravity now, like right? Something like it was the gravity close there. The gravitational force of attraction between the mass of the satellite and the mass of the Earth. Right? So the force of attraction between these two things here, separated by a distance r, right? Correct? So therefore, centripetal force is given by that Newton's force of attraction between the satellite and the Earth. That's okay? So what we're gonna do now is develop something called Kepler's law. So what is here? Centripetal force of this particular satellite is what? Mass of the satellite by omega squared by r. Oh, remember this? We did this last week.
Yeah.
You remember centripetal force and you do all them questions last week? Yeah, remember that?
Yes.
I hear that you getting them right.
It's funny.
And you have to test this week?
Nah, we got this.
Yeah,
Alright.
but that's
Whole
not
week, a whole
everything.
We got the same one before.
Oh, okay.
First example.
All right. So centripetal force is given by this, right? Remember this form? Well, even if you don't remember,
Yeah, I remember.
this is the form of centripetal force, right? And Newton's law of attraction is given by the mass of the Earth, by the mass of the satellite, by Newton's law of gravitation all over r squared. Separation squared. Centripetal force is equal to Newton's force of attraction, right? And this is the formula we tested. You would recognize that this and this will cancel. The r's will come up here. So you'll get omega squared r cubed is equal to GME. That's okay? Yeah. Bring the arrow. Yeah. Huh? Yeah, so I just like a cross multiply. R by r squared is r cubed, right? If I cross multiply, the m's will cancel, right? So when you reach here now, right, what Kepler was able to show, Kepler was able to give a relationship between the period of the orbital part and the separation. He was able to give a relationship between both of them. But he was able to observe the way planets, planets were orbiting as well, and check the separation. And he was able, yeah, he was able to take a look at the planets and how they were orbiting around the sun and things. And he was able to work out a relationship. And then he proved it using this. Right? So he was able, from here now, we know omega is equal to 2 pi m t. Right? So omega squared will be 4 pi squared m t squared. So if I drop that in here now, so we will end up with 4 pi squared t squared multiplied by r cubed is equal to g by mass of the earth. That's okay? If I try to make t squared the subject of the formula, cross multiply, I'll get t squared GME is equal to 4 pi squared r cubed. If I make t squared the subject, I'll end up with this. Right? So here's what he really observed. He said that since 4 pi squared G and M are constants, because this wouldn't change, this wouldn't change, this none of them would change, right? He said that t squared was proportional to r cubed. That's Kepler's law.
So what did you go with it? So then you get so okay. What is it? T is proportional to r squared.
T is proportional.
R squared.
How are you getting now? Yeah, but then you will get 3 on 2. Right? So you can just leave it like that, right? So period squared is proportional to r cubed, right? And this is basically what Kepler showed. Are you okay with that? Right? So remember, Kepler basically said, Sylvester, Kepler basically said that the centripetal force provided for this orbital motion is equal to the what? Force of attraction between the satellite and the Earth. All right. Copy that on class now. But you need to be able to do that, right? Anybody remember what that geostationary satellite? Yeah. But and period of the same period of the Earth, which is how much?
1 day.
24.
Yeah, 1 day as good. Yeah. 1 day. I think I'm not aware.
Make a note of that, right? It's in your hand, though, bro. Right, second. Make a note of that there. Page pay attention. It's mentioned first here. Take up when it is kind of quiet. Feet not here. Feet on down. Feet on down. Especially feet, but she shouldn't do anything on that. Finish. One without the end. How long again is out? Capacity time on them.
10 more minutes.
How you know? You watch that?
Yeah.
Who when was it? All right, so that's Kepler's law there, right? That's one talk a little bit gravitational. I mean, geostationary satellites, right?
And then we get the most.
Actually, basically geostationary satellites, right? But created 24 hours. So a geostationary satellite is always at the same point. So if you look up, you're gonna see that satellite all the time.
You can see it.
Yes.
No, well, it's right. It will be there all the time, right? So right, so a geostationary satellite always at the same position. And very important that the period of that geostationary satellite is 24 hours, right? So the period of that geostationary satellite is 24 hours. So here's what's technically happened. I tried that 3 times or not? 2 hours off. I've tried about 3 times before I get up. Right. So here's a we could figure out, right? If we want to get a geostationary satellite, something with a period of 24 hours, right? What do we have to adjust? What do we have to make sure that that satellite has? What should get it, right? So we want to get a period. Look at the relationship here. We want to get a period of 24 hours. What do we have to control to make sure that that satellite ends up with that particular period?
Radius.
Right. Right? We have to figure out, we have to put it at the exact radius away from center, technically. Right? Not really radius, separation, right? Here. But yes, so we have to make sure that we place the satellite out at that exact position before we let it start to move. Okay? So here's what you're going to do for me now. Calculate R. Right? Use the mass. Use the mass of the Earth at the same value I give you. What was it? 5 point. 5 point, what was it? 5 point, what I gave you? 5.97 by 10 to the 20. Right? So use that value for me and see if you could find the separation from the center or the radius of that part. See if you could find R for me, where that geostationary satellite has to be placed. Right? So you allow it to go up into space, and when it reaches there, you allow it to start with a what? That would be kind of hard. But what you will do is you'll allow it to start with the right angular velocity to maintain the path. Right? So technically, when it reaches the right distance, it will start to move with a velocity v. That would allow it to maintain omega to keep that path. All right? As I when you watch satellite, you will see any boosters or anything.
Any what?
Like boosters or yeah, the way to have.
So yeah, it's faster.
Which one?
Yeah,
Slightly, like
so.
Some of them you want to calculate. So we can't use it for like to send signals that we think that we need to know where they are. Those will be geolocation. Remember sometimes the water and and know what you want speed, so you will just go up there and so that it will. Fine arts man. One quick question. Period has to be in what? Period has to be seconds, right? Right, though work with 24 hours, right? Period has to be in seconds. Come on again. That bigger problem. I give you a little. Ready? If you can compile it. It's a big value, right? By 10 to it's like about 10 to 7. It's a big value. It's like 42 by 10. Okay, that's not wrong.
Yeah.
That's not what we thought about.
I'm not sure if I'm correct.
Well, they go online.
Probably like that, like something, yeah. Around
Anybody, Katrina? Right, so what I can do here in the meantime is I can make R the subject, right? So for R will be T squared by GME all over 4 pi squared. And I'm gonna cube root this whole thing. 24 hours by 60 minutes by 60 seconds
Feels funny.
by G. What gave you G again, Oliver? It's 6.67. I gave you 6.67, right?
Yeah.
By 10 to the minus 11. And then we're using 5.97 by 10 to the 24. All over 4 pi squared. How much you got? What you got, pick up? Pick up, you ain't doing nothing, man. Hurry up now.
One point two by 10 to the something. Something. What do you get?
I don't think it's something on the there are some.
Yeah, I think no. That's right. Yeah.
Tell me what 4.1 by 10 to the what? Minus?
Yeah.
Minus? Oh,
So you see, given this answer, we'll see. I guess it's a little different.
we're again. I got it.
So I got 4.2 and then 2.
Right, I can do it. It's put by 10 to the satellite. Right, so that's how far away that the satellite has to go to maintain this geo stationary orbit, right? Anybody get that one line? Quick, by chance, you got up?
Darren, say bye. Oh no, Sylvester, the gang say hi. What gang? What gang?
I say I will.
I from the gang say hi.
Bit excuse, you mentioned the answer you got it.
So make it time. It's any answer take it.
Alright, so these are things that we need to know, right? One last thing I want you to do from us. Might be a little challenging, but don't worry to explain what it means, right? But see if you can develop some updates. Right, in real short, explain what is meant by geostationary satellite. Don't worry with that, but I will try this some. Show that the radius of the orbit of a geostationary satellite is independent of its mass. It really is. Right now, what do you think about that?
So put that in and see if you see what's up.
Yeah, that's very same thing.
Not on this calculator, so
You know what I'm saying?
We have a paper for us.
Right, and see.
I use the real brackets.
Show that the radius of the orbit is independent of its mass. Right? Technically, it's right there, but I want to see if you can explain how come it's right there.
See, they get answer. I think you got fine.
Oh, shucks, I didn't square T here. Huh?
This way. Oh,
You know, it's such a false right?
sure.
Yeah. Sure.
Sure. He got it. Say it, that bad
Okay, take it over. Yeah. Sorry.
So, that's the order. When you have some, bring up the wrong points and see, because I'll be talking. Yes, like I think it was like we go down to the,
Yeah.
yeah,
Thanks, you're very well.
right. But this, because that's what all this popular. You know, they see the
Yeah, I was going to see that one.
What point did it end?
That's sure.
Well, okay, I do like it 2 million then, or 70% force, right?
Yeah.
Yeah. Yeah. Always active for what center.
Because I got.
So what happens then?
So.
So the same thing, it concern.
It's not like all the good, right? Get up and down, right?
Yes,
This, it's in the abstract characterization of experience of life. I always start with
Okay, that can kind of pass. What you can also see here is this, right?
Yeah.
If you look here, if you look from this point in time here, right? When we made the substitution for gravitational, remember they wanted to show that the radius is independent of the mass of the satellite, right? There is. So as soon as we went here, what happened? Mass of the satellite cancel off. So from this point onwards, we recognize that R was independent of mass of the satellite. Right? If we make R the subject here, R is dependent on what? Mass of the Earth and omega squared. Not the mass of the satellite. Right? Technically, because they can. So you could use this and show them it. Watch here as well. If you were to make R the subject, what's this one here? If we made R the subject, right? For an object moving in a geostationary satellite, R is dependent on this. Right? R is dependent on the period it's moving with the constant mass of the Earth and well, the constants again. So it's not dependent on the mass of itself. That's okay? So if you want, you can start here, show them this, and tell them for a geostationary satellite, R is dependent on these things alone. Okay? Make a note of that now. All right, so those are the things that we need to know about a geostationary satellite and about.
So what are we making on
Just right with arrow. Right,
that?
but
Down that.
right is again for this one.
Yeah, so. Good job.
All right, online. So that's the reason why the radius of the orbit of the geostationary satellite is independent of its. Right. There was a question, right? In 20, I'm not for the
Yeah.
right? There was one small question. After this, all we have to do is kinetic energy and thing, right? So I might want you all to read up on that part of the simply from 4.5. Right? Kinetic energy, potential, power. Right? You'll just read up on that, right? All right, in 2015, there was one small question. I wanted to try and the first, go over the first part. The first part is what the definition, right? Right, try this, please. Last question on it. This is 2015. Yeah, we got 50 different Hey, come on, last thing. 6.42 by 10 is 23. Yeah. 6.79 by 10 to the 6, 6.42 by 10 to the 20. What I got the first one?
Wait now, boy.
Good. Right, remember weight is mass by gravity, right? So we have the mass of the rock.
Because some people are not
Just ask to do a-
what to do.
Right, so we had to find one. Gravitational force, right? I just find G again. Gravity. G is equal to what? Gravitational field. Huh? F and M, but we don't have it. So what's the next version? I just get G.
G is equal to big G,
Big G by,
M, big M,
in this case, big M is what?
mass of move.
Mass of moon,
Mass.
right? Mass of Mars. All over R squared,
R
right?
squared, that R squared means thing, yeah, thing. By thing.
Right, you gave it diameter, right?
Yeah, I see it by thing.
Yeah.
Yeah, that's the break. I'll break it to the.
50, right?
Second there. So, I guess. 3.71. 3.72.
3.72.
7.2.
Yeah.
2.
2.
Yeah.
Way.
3.7.
7.8.
Mass.
And then multiply, I get 5.201. That's the record.
Converted when you think about it, bro.
It's half of it in the square, right?
Wait, wait.
That's half of it in the square. Half of it in the square. So this whole thing half and then square the whole thing. We're trying to go. Take away R and then square. Find button and then square. Divided by 2 and then square. Right, so therefore, you would have gotten 1.4 by 3.72, right?
I get 5.2.
5.21. Right, nice. Now they want you to find the gravitational potential energy. See if we can find the gravitational potential energy, the symbol that they use is U, right?
Gravitational potential energy of Europe. Right.
Remember M by G by H, right? Technically, that can be simplified a little bit. I didn't do the simplification. I'll help you out, okay? How do I help? I am on screen. Right? Capital G by big M, small m over R. Right? If you use the relationship yeah, potential energy is mgh and you plug in the little formulas, they'll end up with it. Right? So use that from an G, big M, small m, all on that. All
I
in,
can just use MGH.
huh?
I can just use MGH.
Try it, but you don't have H, so you don't have an value. Try it and see.
Leave out H.
Very rocket. Right, it should get the same thing.
Yeah. Yeah.
So there's something set.
I do not know. But I'm doing long things are doing testing.
Right, so plugging in G, the mass of Mars, mass of the thing. What was happened 96.7, right? Behind.
Shoot sequence of 19 like 10 to the power 6 over 2. Yeah. You know, I tell you I got 176. 1765.
Yeah.
But the answer on here, 24.
Fine, again,
I get 1.77 here.
like. So if you multiply it 5 points no, let's check in something. If it again in that way, right? That's not what happened.
So I get that with the norm, the MG. Not the MG, sorry, I use U. I use G and M on R.
And again,
And I get the MG is no it is.
no, I just use that to you.
Yeah, straight then.
Oh, okay. So you multiply 5.01 yeah by half of 6.679 by 10 minutes. So if we use this as mg 5.201 and multiply it by half of it.
Yeah, I use it on some phones.
Oh. Okay, that's right. I don't flavor. You can very well. All right. So if you multiply it out, you should get up 12, right? Even if you use mg by h, where h is half of this, you should be able to get the same value, right?
Yeah.
Right? Remember they have the potential energy of the rock, right? So you find the weight of the rock by separation. All right. So just one thing I want you to do, come on. Well, we kind of use it there already.
So I get minus. Yes, so I get minus.
So that is a relationship with the people. So just the minus.
Yes, it's only positive.
No, it's minus.
Yeah.
All right. So one of the homework ones. Yeah, here's what you have to do. All right. Just I want you to read up on work. Same thing from before. Work, energy, and different types of energy, right? The only thing that's new here is that remember what work is, right? Remember, work is force by the distance moving in direction of the force of the object, right? So if you remember this, right? If the force acting at an angle theta, that the work done is f cos theta by the distance traveling. All right. So you just read up on that, and that will take us to the end of this module, right?